So yeah, welcome everyone to our fifth coding session in Type 2 Deep Learning. This one is again a continuation of our attention mechanisms discussion, which we started in our last session. So this is the session's plan, the whole plan for the 6 sessions. We are currently on the 5th session, and we have covered all these basics of machine learning, CNN, RNN, and attention. This is the second session on attention. Okay, so let's begin with the first part of this session, which is the theory. So this is just a rough outline of what all things we're going to discuss today. We'll start with just taking another look at the embedding and attention mechanism, followed by self-attention, what is multi-head self-attention, and how transformer architecture is. Then we'll talk in detail about, we'll spend a lot of time actually today on all the details of transformers, starting from encoder, decoder, the residual connections in it, positional encoding, and then encoder, decoder attention, and all the different layers. And then towards the end, after all this, I have a few slides regarding some advanced topics, some topics after this, which you might be interested in, like BERT, and some other commonly used types of embeddings, rather than the simple ones we've been discussing so far. So this is just the agenda. So let's begin with these initial top 3 topics. So embedding, as we have been discussing in the past few sessions, is just a way of going from any text, so this is French, to a vector. So text is human readable, but it's not actually machine readable. So we basically convert this into a vector with numbers in it. So the vector length can be, so we can decide the vector length, we can decide, which is also called the embedding length. It could be 4 numbers. It could be a vector of length 60. It could be a vector of length 128. And we just convert all of the text we have, each word, into that particular representation, which is called the embedding. So here we are just seeing it for 3 words. And there are many ways of converting or generating these embeddings. One we have looked at in the past is one-hot encoding and some other things. And I have a few slides on some advanced embeddings towards the end of this. So this is another thing we've looked at in the previous session. So attention scoring functions. So we have this function alpha, and then it takes in 3 inputs. One is the query, other is key, and the value. We apply this function alpha on query and key. It could be a softmax function. It could be a different function based on what scoring function we want to use. So we basically operate a function on query and key and multiply that with the value to generate this whole attention score. So this is what we have seen. The difference when moving from this attention scoring function to a more specific self-attention is that in the case of self-attention, query, key, and value are same, basically. So the same vector is being used to generate query, to generate key, and then generate value. All of them will be fed into this function in the same way, and that is going to generate the attention. And because it's the same vector which is giving rise to a query, key, and value, we call it self-attention. So in the previous case, in the last session, the query, key, and values were the encoder hidden layers, the decoder hidden state, and the context vector. But now all of these 3 would be originating from the same vector. And that's the basic idea behind self-attention. So this can also be seen in this representation, where again, in this top right one, we have RNN. So each input will contribute to a hidden state, and that moves on to the next time step. We'll give it the next input, that moves on to the next time step. We give it the next input, and so on. So that has to be done serially, because every hidden state is going to be given the input serially. So t equal to 0, t equal to 1, t equal to 2. While in the case of self-attention, as you can see, each hidden state or each next state is getting inputs from all the different, is getting its input from every possible input available simultaneously. So in this scenario, this is getting inputs from all of these vectors. This is getting input from all of these. And in this way, we can generate all of these different nodes in parallel, because they don't depend on each other as such. They're depending on just the inputs. So you can also generate all of these together, and the logic is a little bit different. It's not using a context vector or a hidden state from outside. It's just using this x1 to generate all 3 things, x2 to generate all 3 things, which is the key, query, and the value. And then this is just a conventional CNN we are familiar with. So each node is going to be getting inputs from some a subset of the previous inputs. And then just an extension of the attention is this multi-head attention. And the only difference here is that instead of calculating the attention once, you use query key and values, but you apply a bunch of, you apply these fully connected layers to generate the attention. So this is the single block here will represent a single block of attention, but then you do it a bunch of times. So you do it 8 times, or you do it 16 times, or a whole lot of times. That will give you a whole lot of different weights for each fully connected layer. And that will give you different ways of estimating attention. You concatenate everything, apply a fully connected layer to get a reasonable sized output which you expected. So just using the same attention head multiple times, that gives you the multi-head attention. And in the case of self-attention, queries, keys, and values will just be same. So that's the only difference. So you just use one head of the attention block, and you apply it a couple of times, concatenate the output, apply fully connected, and that gives you the output. That's the multi-head attention. So now we have seen these top 3 parts. Now let's look at what transformer architecture is from the very top, and then we'll dive in under each step to see each step of the transformer network in detail. So again, we are familiar with this. So transformer is at its very core just an encoder-decoder based architecture. So you have an encoder which takes in the input. It generates something, it generates an output which goes into the decoder, and then decoder generates an output, which basically is our translation or whatever application we are working with. But the difference is transformer actually does not contain just one. So the original paper of transformers suggested this stack wherein you have 6 encoders and 6 decoders. This number 6 is not special. You can have more, you can have less, you can even have larger decoders or larger encoders. But this is just one of the designs. So you have, instead of one encoder block, you have 6 encoder blocks. Each encoder block will get, so this one will get an input from outside and then pass on its input to the next encoder block. And then the final one will generate an output, which will be fed inside all the decoders. And then the decoder will generate an output, which is basically a translation or whatever application we're working with. So this is an encoder-decoder from inside. So encoder block itself contains 2 other blocks. One is the self-attention block, and another is a feed-forward neural network. And the decoder contains the same thing, self-attention and a feed-forward neural network, but it also contains an encoder-decoder attention block. So let's look at all of these things in detail. So let's start with encoder and its self-attention. So just to remind you, encoder has self-attention and feed-forward. We'll firstly look at self-attention, and then we'll move on to see what feed-forward neural network is. So yeah, so this is just, again, the same thing. So we have some input, x1. So let's say we want to give it 2 words as input. So thinking machines. This is the first word. This is the second word. Both of these words will go inside self-attention. That will generate some output. We'll call it Z1 and Z2, which will then be fed into feed-forward, which will then generate another output. Let's call it R1 and R2. And that is going to go inside the second encoder. So the advantage here is that, so self-attention requires input from everything, right? So to calculate the self-attention, like I said, we will need x1 and x2 both to calculate Z1, and then we'll again need x1 and x2 both to calculate Z2. But Z2 does not depend on Z1 in any way. So we can compute Z1 and Z2 parallelly because they just require x1 and x2. And again, we can pass on these Z1 and Z2s to this neural network parallelly and then just generate R1 and R2. So each word and this, what it's called in this way. So with each word or each pathway can be worked in independently or parallelly. So that's the advantage with this architecture as well. So another look at self-attention. So the idea behind it is if you have a long statement, and let's say you have the statement where you have this word it, self-attention will take care of what this it refers to, whether it's the street or whether it's the animal or whether it's something else. So because you want to understand the context of the context and the objects which have been mentioned in the sentence previously, you want to take care of what these different words correspond to. So self-attention just encodes that idea and takes care that this it is actually talking about the animal and not the street. So let's look at how it's computed. So the math and the matrix multiplications and all that. So let's say again, we have the same 2 inputs, thinking machines. This is x1 and x2. And as I said previously, in self-attention, we compute the query key and value from the same input, right? So we'll use x1 and we'll compute 3 vectors, q1, k1, and v1. So query key and value generated from x1, and same query key and values, similarly query key and value will be generated from x2. And how we'll do it is we'll just pass this x1 to a multilayer perceptron or a fully connected network. So let's say we want, our input is of length 4, and we want to generate a query vector of size 3. We'll pass it through a multilayer perceptron with 4 inputs and 3 outputs, and just generate this Q1 like this. And again, if we pass X2, that will generate Q2. So we'll just use the same multilayer perceptron for queries, then we'll use another one for keys, then we'll use another one for values. And from each input, we'll generate 3 vectors. Then we'll operate on the normal, like using that attention scoring function, we'll just operate those operations using these query key and values. So we'll take a dot product of query with the key. So Q1, K1, Q1, K2. We divide it by the length of the embedding. This is just to stabilize the gradients. We take a softmax of that. And then we multiply that with the value. So this is exactly the same thing which we did. But in the previous case, query keys and values originated from 3 different hidden states or outputs or vectors. Here, query keys and values were just generated using this x1. So we use x1 to generate query key and value. We take a dot product of query with keys. So query 1 key 1, query 1 key 2. So these 2 things. Then we take a softmax of that. We multiply it with we multiply that softmax value with the vector value vector. So v1 and v2. And using that, we sum those 2 vectors to generate z1. So as you can see, both k2 and v2 are being used to generate z1. And similarly, k1 and v1 will be k1 and v1 will be used to generate z2. So each word to generate a self-attention, each word will take in the query key and values for corresponding to the other words, and that's how it's able to connect those, make those connections. And understand the context of which word depends on which other word in what way. So, throughout the slide, so wherever there is a fully connected layer or multilayer perceptron, I'll just use this symbol to show it. And the sizes of that could be different, but this is just a simple representation to remind that we are using a fully connected layer to generate the output. So like I said earlier, same input, apply 3 different fully connected networks, generate query key and value. Those query key and value are fed into this to generate the attention score. So once we have that, we basically take a dot product of query with key, divide it, take the softmax, multiply it with the values, and get the output. So as you can see, because these are matrices, you don't have to do it word by word. You can just do it for both the words together, and because these are matrix operations, and parallelize it. But why do it just once? We can, like I mentioned, multi-head attention. So you can do it a bunch of times. So you apply the fully connected layer once, and we can generate it. We can generate one set of query key and values. We apply another set of fully connected layers, fully connected networks, and we can generate another set of query key and values. So using this, we can generate many, many different heads, attention heads, or many, many different sets of query keys and values. In the conventional transformer or the original transformer network, this is done 8 times. So that gives us 8 outputs. So using the same input, the same 2 words, thinking machines, applying those attention heads 8 times, we get 8 different outputs from Z0 to Z7. But the problem then is we want to pass all this information into a feed-forward neural network, and the feed-forward neural network is expecting this smaller size, not the size of 8, not the 8 times size which we have. So what we do is we concatenate all these 8 outputs, and we multiply it with a weight matrix that was trained jointly with the model. So again, multiplying with the weight matrix simply means that we pass it on into another multi-layer perceptron so that we can use all of this, we can get a desired length output. So if this is a 64 length and we need a 4 length output, then we'll have 64 inputs here, we'll have 4 inputs here, and we'll just pass it on to get the final output, which will be of a relevant size. And then we can pass this output into the feed-forward neural network. So this is just a recap of the whole process. We either get an input from if it's a first encoder, we'll get the input as words which have been embedded. If it's a downstream and or an encoder in the inside layers, then it would be getting an input from the previous encoder. So either using X or R, we apply a whole lot of different attention heads to generate different sets of keys, queries, and vectors. We apply different query key and vector weights to generate query keys and vectors for different heads. Applying the attention scoring function, we generate the attention scores, and then we concatenate it together, apply another fully connected layer, or apply another multi-layer perceptron to basically generate the output of a desired size. So yeah, so let's now move on to the feed-forward neural network. So the first step of encoder was self-attention, which gives an output which goes inside feed-forward neural network. And feed-forward neural network is simply just a fully connected multi-layer perceptron with some inputs and outputs. And this Z is what we got from the previous layer, which is fed inside this full feed-forward neural network and is passed on to the, which gives an output which can be either passed on to the next encoder or to the next decoder, if that's the next stage. And then these different layers also have residual connections. So let's look at those. So this is again the encoder. This is the self-attention, and this is the feed-forward neural network, which we have seen. But after the self-attention, there is another step, which is add and normalize. So there is a residual connection around this self-attention, and there is a residual connection around this feed-forward as well. This actually shows it in a better way. So we have these two inputs, again, the same inputs. They are passed, the embeddings of these inputs are passed inside. The self-attention is applied using these two that generate Z1, then it generates Z2. Then because we have a residual connection, we add this actual input X with this generated output of the self-attention. We take a layer norm. So layer norm is similar to batch norm, but let's see how it's different. So in the case of batch norm, we take the averages, we normalize the examples. So if we have a batch of 32, or we have a batch, we basically normalize the batch. So if we have a bunch of examples, we normalize those across those examples. While in the case of layer norm, we normalize it across channels. So we normalize the features across this whole sentence. So if we have a sentence of 5 words or 10 words, we normalize it across, we normalize the features across that. Instead of normalizing across different examples, like we do it in the batch norm. So we add these, we add this residual connection, we take a layer norm, we pass it on to the feed-forward network. And then feed-forward network itself has a residual connection. So the output of the feed-forward is then added again to this Z1. Again, we do a layer norm, and then it gives the output, which can either be passed on to the next encoder or it's passed to the decoder stage. Now let's look at the positional encoding. So one sort of a problem with the whole of this is that we have not encoded how the words are ordered in our sentence, right? In RNN, we were giving the words in time. So the second word was followed by the first word. So first word would go in, generate a hidden state. Then the second word would come in and generate and modify the hidden state and so on. But in this case, we are passing the whole sentence together. But we also need to make sure that we encode the information about the order of those words somehow in the neural network or in this whole architecture. So this positional encoding is used to do that. And one way to do it is that we generate, based on the indexes of the words, we generate these weights, or we generate these different vectors, which can then encode the information of where the word was. So this is just one way. There are multiple ways of doing positional encoding. So let's say we have a different word. So let's say we have 60 words, and each of our each of the word embedding is of this length, which is given by this x-axis. What we'll do is, for each word, for ith row, which is ith word, and jth column, which is its encoding number dimension, we will use the sine and or cosine function to generate what its positional encoding should be. And then we'll just add that vector to the word embedding. So this might sound complex, but let me show it in a better way in this slide. So let's say we have 3 words, and we generated their embeddings, x1, x2, and x3, and the length of their embeddings is just 4. Then we will generate, for each word, we'll also generate its positional encoding based on the formula I showed in the previous slide. The length of the positional encoding will be same as the embedding size, and it would just encode where the word is positioned. And because this would have an I of 0, this would have an I of 1, this would have an I of 2. So ith row, so 0, 1, and 2. And then J is just their position. So J0, J1, J2, J3. And feeding in all this information in the previous function, we can generate these positional encoding vectors. So before we pass on this embeddings of the input to the network, we just add the positional encoding to the embeddings and then pass it along inside the encoder. And then the idea is that the keys, queries, and the values generated after this would take care of using these positional encoding. The key value, key, query, and values generated would take care of the fact that the words were actually ordered in a particular way. So that's the idea of positional encoding. Now let's look at the final part of the transformer network, which is the decoder block. So just to quickly recap, transformer contains an encoder and a decoder. Encoder takes the input, passes on some output to the decoder, which gives the output. And transformer actually has 6 encoders and 6 decoder stacks. And we also saw that encoder has a self-attention and a feed-forward neural network. And decoder had a self-attention, encoder-decoder attention, and a feed-forward network. So let's just begin with the decoder. So yeah, so we are passing in some input to the encoder, which passes it to the next encoder, which gives an output. This output is converted using a multi-layer perceptron to keys and values. These keys and values are then passed to the decoder, along with the decoder's input itself to generate the output. So let's look further. So basically we give an input I, which was the first output of the decoder, using the keys and values encoded from the encoder, and the previous word, we generate the next word, and that cycle keeps on repeating. So this is very similar to what we saw for the conventional RNNs. But let's actually see what's happening inside the decoder and what this linear plus softmax is. So as I said, decoder has three different kinds of layers. One is a self-attention layer, which is exactly the same as what we have discussed. So given an input, generate key query values using multi-layer perceptrons, apply multiple heads, concatenate them, apply another layer, and generate an output. So this is exactly the same as we have seen. And the speed forward is exactly the same. Again, a fully connected multi-layer perceptron, which can convert from any input dimension to an output dimension of our choice. This encoder-decoder attention is something different from these two, which is very slightly different. So as we have seen in the previous slides, this is the attention scoring function. We have a query, key, and value. And in the case of self-attention, query, key, and values were just same, right? So the same X was used to generate query, key, and value. In the case of decoder and encoder-decoder attention, the keys and values are actually used from the encoder. So the encoder of the first step gives the output of the encoder is converted into a key vector and a value vector. This is actually passed inside the input to the decoder. And instead of using the same vector to compute query, key, and value, we just compute a query using the input vector and use the keys and values as is from the encoder, and then generate the attention, which is used in this encoder-decoder attention step. So then the final step in this whole chain is this final linear layer. So because we want a word output, right? So we have the output of the decoder stack, which would be again a vector. We apply a fully connected layer or a multi-layer perceptron, which gives us an output. So let's say the decoder output is of length 64, and we want to see what the probability of each word in our vocabulary is. And let's say our vocabulary had 100 words. So we want to see how probable each word could be to be this current output. So we'll apply a linear layer, which would have this 4 input, which is the output of this decoder stack, and 100 words as the final output. So it will encode this information and give us 100 numbers or 100 logics as output. We apply a softmax because we want to see the probabilities and we want to see which one is the most probable. And let's say this 5th index is the most probable. We'll apply this, we'll get that this 5th index is most probable. We'll see what which word this index corresponds to, and that's our output. This is very similar to what we did for RNNs as well. So we just used an output of the decoder stack, converted into the length of vocab size, applied a softmax on it, and the highest probable word index will give us what word it corresponds to. So this is just to recap the transformers. So let's say we have a transformer with 2 encoders and 1 decoder, or actually 2 decoders. So you have some inputs, we apply self-attention on it using both of these, which will compute key query values. We add a normalize because we have a residual connection here and a layer norm, pass it on to feed forward, again, a residual connection and a layer norm. Those outputs will then be passed to the next encoder. The output of the encoder will be converted into keys and values. These keys and values will be passed inside the encoder decoder attention step of the decoder, while the previous steps of the decoder will just take some start of sequence input, apply some self-attention on it, add a normalize, apply this encoder decoder attention using these keys and values from the encoders, again add a normalize, again feed forward, pass it on to the next decoder, generate an output vector, apply a linear to generate an output vector of length your vocab size, apply a softmax on it, and decide which word is most probable to give the word prediction. So this is the whole chain. This is another way in which it's typically shown. So this is from the original paper, which suggested the transformer networks. And this is the image which we have been using as our cover image for D2L as well. So now we have seen this. Again, it's the same thing. This is the encoder. This is the decoder. You can have n number of encoders. You can have n number of decoders. And you have multi-head attention instead of just a single head. And then you're using scale dot product attention. So yeah, I'll again pause here for a little bit and take some questions, and then we can move on to the further topics. Actually, I have 2 more slides. Let me just do that first. Sorry. So let's see how we do training for these. So let's say we have a vocabulary of 5 words and an end of sequence. So we'll have these 6 indexes. We can one-hot encode these, just a simple embedding. So we can one-hot encode these and say that am would be represented by this vector. Then we initialize our whole model with untrained, with just random weights. We give it an input, and let's say we want the desired output to be thanks. So we want this as the desired output, which is given by this vector. We gave it some input, and this is the output it gave us. So we just compared these 2 vectors. And like we mentioned previously, we can just use cross entropy loss to compute what the loss is, and then backprop the gradients to see, to modify the weights till it gets better. So let's very quickly talk about BERT. BERT is again it has a whole lot of new things, but I'll just talk about it very briefly because then we want to move on to the coding session. So BERT is bidirectional encoder representations from transformer, it's just the full form. It is basically a trained transformer encoder stack. So transformer, as we've seen, had a bunch of encoder stacks with a few decoder stacks connected together. BERT is just the encoder stack part of this whole thing. There are 2 sort of variants of BERT. One is BERT base, other is BERT large. This one has 12 encoders, this one has 24. So these are pretty big models because these encoders themselves are pretty big. So, so the sizes of the feed-forward networks and the sizes of the inputs, sizes of the dimensions are much larger than the encoder originally proposed for transformers in these cases. So each of this encoder is bigger than the encoder we have seen previously, and we have more number of encoders here. The basic idea behind BERT training is this. So there is a 2-step training process. One is the semi-supervised training. So what we do is we have this BERT model. This is just encoder. We get some data set, basically like a book or hundreds of thousands of books or the whole Wikipedia or the whole Reddit. So basically a whole lot of text. We pass that input statement by statement or in some particular fashion as the input to the encoder. But what we do is we mask, we do randomized masking. So there are multiple different ways of masking. So we mask some inputs and we ask the model to predict what the word should be in that input. So let's say we have a statement of 10 words. It's a coherent statement of 10 words. We mask the 5th word. And now we are asking this encoder network to predict what that 5th word should be. And we are training it on that. We are training it on how good a prediction it's making. So it's a semi-supervised learning because we don't need, because we don't have any base classes or anything. We are just using the statements we had. We are masking some of the words, or we are sometimes replacing some word with another word. And we're just asking the model to predict what that word should be. This way it can learn the language. This way it can learn the various representations. It can learn how to encode different words, different structures used in the language, different relationships in the words. And once this model has been trained in this way, then we apply a supervised training task on it. So for example, we want to give it a statement, and we want to predict whether it was a spam or it was not a spam, we can use one of the outputs of the encoder layers. We apply a simple fully connected layer on top of it, and then we give it a labeled data set. We train on top of the all pre-trained network with this labeled data set, and that to predict the spam versus not spam. And there are many different applications. We can compare words, we can ask a question and see how two statements are related. So there are all sorts of different applications, but this is the basic idea. We train the model using a semi-supervised approach, using a whole lot of data, a whole lot of sentences, and then just apply some outputs, some layers or fully connected networks or multi-layer perceptrons on the output of this encoder for whichever task we wanted to do. This, as you can think, is very similar to the fully connected layers we see in CNNs. So again, this is the BERT, which has a whole lot of encoders in it. We give it the input, and we give this special token as the first token, and then we start the actual input process. We train this whole thing as the semi-supervised step, and then corresponding to the output of this first token, we apply the classifier layer or the fully connected layer, like we do for CNNs, and that gives us the final output. So this can have two outputs if we want if we want a binary classification. It can have multiple outputs depending on how many we need. And then just 2 slides quickly on some embeddings. So embedding, first way is the word-to-vec, wherein we have, so one-hot encoding and other encoding embeddings we've seen so far do not actually understand the relationships between different words. So king, man, and woman, these things have something common, right? All of these are human. And then, so women, and like Devansh once showed in his slides, that king, queen, man, woman, all of these should have some common things. But if we just encode them as different indexes on a simple array, then that relationship is not being encoded. So word-to-vec is a way in which these meaning-related relationships have been captured. But the problem with this is it predicts the same word regardless of the context. So we can have same word which is being used in different contexts. For example, we can have the word bat. It can represent different, it can have different meanings based on where it is placed in the sentence, what the context is. So that's the downside of using word-to-vec. It does not have different outputs, different embeddings based on the context. And to overcome that is ELMO, which actually consists of 2 LSTM layers. It's actually a bidirectional LSTM, and it uses the whole sentence. So it uses this whole sentence, for example, let's stick to understand what the embedding of stick could be. So stick can have multiple meanings. And based on what the statement or what the sentence it is placed in, this ELMO uses that sentence to decide what the embedding of that word would be. So it generates these contextualized word embeddings instead of just a simple word embedding, a constant word embedding, which would be, which you'll get in the case of word-to-word. So yeah, that's all I had for the theory sessions. There are a lot of different concepts and topics, like details of the BERT model, details of transformers. There is an OpenAI transformer, which you can look into. There are different ways of embeddings and the details of how this ELMO is trained and word-to-vec is trained and how they're used. But we just don't have time to cover all of these, so I would recommend you to look at it. And feel free to ask us questions on Slack whenever you have.
Okay, so welcome to the coding session for Dive into Deep Learning, session 5. We'll be talking about transformers today, or we'll be coding transformers today. So this will be slightly different from what we have been doing in the past. For sessions, we have coded everything from scratch. In this one, we won't be coding everything from scratch. We'll be using some of the or some of the available things in PyTorch. And the reason for that is, although we can code the whole transformer architecture, we can code everything from self-attention to layer norm and everything else. Given the limited amount of time we have, I think it's best that we stick with something which is a bit more practical. So before I get started, I'm just going to give you an overview of what all we'll be doing today, and then we'll just dive right into it. So the task is still neural machine translation. So this is similar to what we have been doing in the last session as well. We were translating from English to French or French to English. It's the same website, different data set. This time we have German to English or English to German. So you can play around with the text over here. We also have the same or similar set of code over here, which is just for tokenizing, applying some regex on top of it. So we won't be going over that again. And also it just started raining and thundering, so there's a lot of sort of noise. Pardon me for that. And this is just again torch datasets. I know we haven't talked a lot about torch datasets, but it's fairly easy to understand. So do feel free to check it out on PyTorch's website. And I won't be going over this either, but what we are just doing is converting this into a data set which you can batch and then take chunks of data from the whole data set and run through. So this is the architecture from the original transformer paper. This is what the encoder looked like. This is what the decoder looked like. We won't be coding parts of it, but we'll be using directly nn.transformer encoder layer and transformer decoder layer and so on. So we'll start with embeddings. We'll do positional encoding, and we'll do the embedding layer. We'll do the encoding layer. We create the encoder with n such layers. Similarly, we'll do the decoder, and then we'll put everything together in a nice nn dot module, which we will train for a really small number of epochs because it takes huge amount of time to train this and see how it works. So that's all what I have for you today. Let's hope we can finish it in next 40-45 minutes so that we can have some questions at the end. Okay, so as I said earlier, all this this is just all the imports which we usually use, all very straightforward, torch.nn and torch. This is connected. Okay. I've already downloaded the data set, so that's why I've commented this out, but yeah, feel free to either change it or download it. Okay. Yeah. So yeah, now we've read this data set. So this just translates. You can go back and forth between German and English, and we'll be using a maximum of 10,000 sentences in this, and then the maximum length will be just 10 of each sentence. So we are doing the same thing. We are sort of converting or tokenizing everything in here. This is what this loop right now is doing. And once that is done, it's just going to give us, it's just going to sort of print a simple sentence over here. Yep. So this is the English version. Is it true? I think so. And then this is the German translation. These are encoding. These are the tokens for that. This is the start of sequence, end of sequence, and since everything has to have a length of 10, it's just padded with this pad token at the end. All right. So now we're gonna just define some of the hyperparameters because this is gonna make our life so much easier when we are trying to code all of these things. The first thing which we need is the length of the vocabulary in English, then the length of vocabulary in German, and so on. So this is actually just length of English words. I have a variable over here which is called English words, which just sort of is a set of all the English words. Similarly, we have all the German words over here. So it just has all the unique words. Similarly, you can just do len of the number of epochs. We'll just keep it to be 15 for training. Hidden size in this case, since we want to keep everything small and simple, is just 8. People I think go up to 2048 or so on. So these numbers can blow up very quickly. Embedding dimension this is the length from which we'll map our tokens to. In the case Kshitij was showing, he had 20 words which were I think embedded into something of a length of 26 or something, or 30, but we'll just keep it 512. Batch size, we're going to keep it 128. Number of heads, this is the number of, so in case of multi-head attention, this is the number of heads in that. Number of layers is how many times you want to repeat these encoder and decoder blocks in the whole stack. So we're going to keep it 6 as the original paper. We can change it. It's not a big deal. Learning rate, this is 10 to the -3. Dropout, so since you're using multi-layer perceptrons, you can apply dropout so that it doesn't overfit easily. And then since we'll be using GPUs, we'll be using torch.device CUDA, and that's it. So these are all the hyperparameters which we'll need today, and we'll sort of fix them and we'll keep calling them again and again so that we don't have to keep putting in numbers. And also you can sort of play with this later on if you are playing with a notebook, or you can change anything or see how changing something affects others. This over here is just creating the data set. So right now we have tokenized all the data which we had. Now we'll be creating a data set out of it. So that's just torch.utils.data.data loader, and finally. So that's very simple. What it gives you in the end, I'll show you what it does. So the first thing we need to do is create an iterable in loader by train loader. And now it's an iterator. So what you can do is source comma target is just, you can apply a next to this, and we can actually print what our source and target is. So I didn't run this. Yeah, so this is what it did. We have set a batch size of 128. So if you actually, the first thing we should do is print the shapes of all these. Okay, so here are the shapes, which is 128 and 10. So 10 is the length of the sequence which we chose, and 128 is the batch size. Now, if we go for something like source 0, then this is the first element of the batch, which will have length of 10, and these are just some tokens. What we can also do is we can go ahead and sort of print or convert this back from token to a sentence. So you can do something like for index in source 0, and let me see what the variable was called. It was called English words. Just gonna add. Otherwise, so I've added this end is equal to a space. Otherwise, it will just print everything in a new line. So when we just run this, so it says he bought vegetables and some fruit, end of sequence, start of sequence, and then pad because everything has to have a length of 10. Similarly, you can do the same thing for our target, which will give us the this target, and now this will become okay. Since we ran it again, okay, print. Yeah. Since we ran next again, it sort of went to the next sequence. Yeah, but the first sequence is I don't like swimming, and this is what the converted German version is. Again, everything is padded and has a start of sequence and end of sequence. So this is what our data set would be today. This is what we'll be using to create this transformer. So the first step is, once we have our inputs, we need to create an input embedding. We also have outputs for which we need to create an output embedding, and then both of them have to be position encoded. So we'll create these two things first, the embeddings and then the positional encodings, and then we'll look into the specific decoder and encoder blocks. So we have a variable here which is called encoder embedding. The other one is called the decoder embedding. And right now, the shape which we had was 128,10, and this 128 was batch size, 10 was just the max length. Now we'll have another dimension over here, which is the embedding dimension. So, okay. So this is just nn dot embedding, and then variables are a number of embeddings in the embedding dimension. So embedding dimensions we have already decided. We have already sort of defined on the top, and we have already defined what is the number or what is our vocabulary size. So that was called, so this is called English vocabulary size, and this is embedding size or embedding dimension. So similarly here, we'll have embedding again. So this is the vocabulary size for German, and then again the same embedding dimension. And this just creates a very simple feed-forward network, which goes from this to that, this dimension to this dimension. And we can actually see, so you can do source is equal to and then did we define a source? And yeah, so we have already defined a source and a target, so we're just going to keep reusing those. So now, so this, and then similarly, target is equal to decoder embedding target, and then we can print the shapes, because at this point these are all randomly initialized, nothing is trained, and anyway these are just going to be numbers which we cannot make sense of. So we'll have source dot shape and target dot shape. So we run this, and yeah, so now we have 128 dot, which is batch size, 10, which is the length of sequence, and then 512, which is the embedding dimension. So now the first part of this whole diagram is done, which is input embedding and output embedding. Now we'll create positional encodings. So this is how positional encoding would be done. So you have a word, this d is equal to 5, and then this is sort of the equation which we use. But this is only for even numbers. For odd, we use cosine instead of that. So the simplest way of creating the positional encoding is just to create an dot module, and which we'll use further. So that's how we have been sort of doing it so far. It's just init, and then cell. I'm gonna explain all of these. So we're also gonna put in dropout and just put a default value of 0.1 and a max length of 5,000. Because you have to do the super method, because you are having an dot module, positional encoding, comma self, and then init that. Okay, so you just create a dropout, which is nn dot. This is just the dropout layer where we'll put in the dropout value. Next, we are going to create positional encoding. So that's just torch dot zeros, and it's going to go from our. So we're going to zero initiate everything and just basically fill in values. So that and this is done. And the way we're going to do it is similar to how you will do it in NumPy. You create like an array of all the positions, which is just np dot arrange or arrange, and similarly we have torch dot arrange, which is what we're going to do here. So this position is equal to torch dot arrange. It goes from 0 to max length, and we want the d type to be torch dot float. We're also gonna add dimension here. This whole business of adding dimensions and permuting, which will be coming soon, was one of the major reasons why we decided to not actually sit and encode all of the encoder decoder blocks, because you have to do a lot of this and keep a lot of track of what is where, like do you have batch size first, or do you have sequence length first, and so on. So these things are only important when you're trying to sort of write up all of these, but not for conceptual understanding. And then I'm just going to write this term first and then explain what's happening over here, because you don't see torch.exp at all in this expression. But I'm going to explain what's happening over here. So it goes from 0. And just make it float. Then this has to be multiplied with that divided by. So that's that. Okay. So we have a term here which is position divided by, in this case, think 10,000 to the power 2 of I divided by d. Okay. And computing this, given that this is going to be an incredibly small number because you're dividing by a huge number over here, we want to be sure that we don't run into numerical instabilities. So what we do is we compute this in the log space, and then we do torch.exp finally. Okay, so that's why it was done in like this way, and that's the only reason, just to have some numerical stability and make sure we don't have issues with that. And now this is one of my sort of favorite Python tricks, is using double colon. What it does is along this dimension, fill or do this for every alternate value. So colon 2 means every alternate value, colon 10 means every 10th value, and so on. So this is how you can jump directly within an array. So you just do torch.sign position times the, and then similarly we'll do this for so the first half is encoded as sign, the other half is encoded, or like half of the values are encoded as sign and the other half is encoded as cosine. So this is torch.cosine, and then so that's that, and then P is equal to, again, some more dimension jugglery, and then finally we do this thing self dot register buffer. And you might ask, what is register buffer and why I'm doing this? So this is, so the PE value or the position encoding value is something which we have to add. This is not a learnable parameter. This is not something which we have to sort of keep track of. So we just register it as a buffer. The reason we do it as register buffer rather than self.pe is because usually these models become fairly large, or you want to use multiple GPUs for training, and that's when you can't just use self.pe because it won't update properly. So this is just a nuance which PyTorch has, which you have to sort of take care of. And since this position encoding block was taken from a PyTorch tutorial, that's why I'm just sort of following that. But now finally we'll define a forward layer, which I think answers Ramesh's question. So what we do is we do x is equal to x plus self dot pe, and this is that. So we do not concat, we compute all the sine cosine values and we just add it over here. And then what we do is we return x, but we also add the dropout. So self dot dropout, and then x. And that just gives us our positional encoding. That's it. Okay. So we'll see it in action over here. So what I've done over here is I've actually put, so let me just plot it and tell you what it is. It's called source. Okay, yeah. So here on the y-axis, this is the dimension 10, which is the length of our sequence. Here we have 512, which is the length of our embedding. And you can see all of these values are the same because probably they're padded. So this is what the original input sort of looks like. And now we'll add the positional encoding on top of all this and see how it changes. Okay, so the positional encoding has basically D model and max length. This is nothing but our embedding dimension, and then the max length in this case is just max sentence length. And then we can again do source comma yeah, we can do this. So what I'm doing right now is just applying the same positional encoding to both source and target. So I can just do one, that should still work. So we have defined PE, which is positional encoding. Then we do again some more dimensional jugglery over here, 1, 0, and 2. And the reason for that is so what we are doing over here is we earlier had batch size, sequence length, and embedding dimension. The way this whole thing is coded, you need sequence length first, batch length second, and embedding dimension after that. So You just have to be sure that you're following the correct dimensions while you're coding transformers, and that's pretty much it. And this should work. It didn't because unexpected keyword max. It's called max length. Hopefully it will work now.
I think you're using maxlen in other places as well. Yeah.
Yeah. Oh yeah, here. Max length. That should be it. Yeah. Okay.
I think you got to change here as well. You're passing max len equal to maybe need to max.
Thanks. Yep. Thank you. Okay. So now we can actually plot this and see what it looks like. Okay. So now you can see there's some difference somewhere in this range. So this is because we have added these positional encoding, the positional encoding on top of it. So right now what we have is we have some data which has gone through some random embeddings, and then on top of it we have added a positional encoding. So this does complete the second part of our transformer architecture. Now we'll do this bit, which is the encoder. So the first thing which we need is this whole encoder block, and for that we'll be using nn dot transformer encoder layer, and then we have n such layers connected together. Okay, so let's go and do that. Okay, so we have encoder layer, which is just given by nn dot transformer encoder layer, and this takes in the model, which is embedding dimension, n head, which is the number of heads, the feed forward dimension, as I said, which we call the hidden size, and then dropout, which is sort of optional. Okay, so we need embedding dimension, we need num heads, we need hidden size, and then we need dropout. That's it. And then we can just do this, and then we feed in our source. So once we do this, it's just gonna sort of encode randomly right now because this is not trained. So we can do a couple of things. First is let's print what this has, and then the other thing which you want to print is, so the output of this goes into a variable called memory, and we're just going to take the shape of that. Okay, so what it does is it has multi-head attention, which Kshitij talked about earlier. Then you have the linear, dropout, linear, layer norm, and then it also has the residual connections in between. So you don't have to do any of these things by yourself. And these number in features is embedding dimension, out feature is 512 again, and then so on. So it sort of takes care of everything. And this is just one encoder layer right now, and we're gonna have n of such in our case, which is just 6. So what we are gonna do is nn dot transformer encoder, and it takes in this encoder layer. So it's encoder layer, and then the number of layer which we have is called num layers, which is 6 in our case. And you can do the same thing again. You can pass in the same input. You can just do encoder and source. We can print what the encoder looks like. We can print the memory dot shape. Okay, so the encoder, so num layer in our case is 6, so it has 6 of such layers. This is 0, 1, 2, 3, and so on. So it creates copies of these. And then finally the memory shape is 10, 128, 512. So this is max sequence length, batch size, and then 512 is the embedding dimension. So this is what we have for our encoders, and this is what this part is, and this is how you would code a transformer if you actually have to do it for any of the tasks at hand which use transformers. The next step over here is the decoder part. So we have already done these two. Now we'll do this and the final output probabilities part. Okay, so similar to nn dot transformer encoder layer and transformer encoder, we also have nn dot transformer decoder layer, which again takes the model which is embedding dimension, which takes num heads, which takes dimension feed forward, which is num hidden, hidden size. Okay, and then drop out. Okay, and similarly we'll have nn.transformer decoder, which will take in this decoder layer, and then the number of layers. So that's num layers. And now we can again print just the decoder layer in this. So you can see again, you have multi-head attention, one which corresponds to self-attention, and the one which corresponds to the data which will be coming in from encoders. So you have two of these. Okay, then you again have linear, then dropout, normalizations, and dropouts, and so on. So this is the decoder bit. And finally, you need a linear layer which will transform all of your decoder output to something which you want to use. In this case, we just want nn.linear. And this nn.linear goes from embedding dimension to the vocab size, which in case is German. So that's just that. In the actually, I'll have to run this to run the next part. So we'll do it's called transformed output is equal to decoder. And it's going to take two things, the target, and it's going to take the memory, which is the output from our encoder. And then we can print transformed output.shape. Okay, so this is 128, 10, 5, 12. This will take in from the embedding dimension and map it to the vocabulary size in German. So you can do dense, and we can put in transformed output, and then we can put final output.shape. So you can see this is now 128, 10, 6892. 6892 is just the vocabulary and dimension or the length of the vocabulary for German in this case. So any questions so far before I start sort of putting it all together and create this whole transformer?
So there's one question. The input, so the input in the transformer decoder from the encoder is memory?
And the target.
Yeah, okay.
So it takes in two things, the target and the memory. I'm going to show you here. Let's go back to the diagram. So yeah, here's what, so this is the decoder block. So you have your targets or the outputs. You'll have the output embedding, positional encoding, and this goes in. And then the other input is this, which is coming from the encoder. So the memory and then the target over here, which will give you the output. So, okay. Let's start putting all of this together because so far these are...
One more question. The target is not exactly from the encoder though, right?
No, the target doesn't come from the encoder. The only thing which comes from encoder is like the output, which is the memory, which we're calling here. It's like the encoded values from whatever input you had given. Does that make sense? Yeah. So this all so right now I just showed you each of the components, and while I'm going to write the forward loop for the transformer, I think this will become much more clearer then. Okay. So I'm just gonna do one simple thing over here. I'm gonna put these two beforehand, and as we add each of the components here, we'll keep adding stuff in the init function. Okay. So we have to do super transformer net cell, and then init this. Okay. So the first step to do that we have to do is going back, which is embeddings for both input and output. And then we need positional encoding, and then we need all these layers. Okay, so we'll start with embeddings, and then we'll go into positional and encoding. So it's coming back here. Now embeddings are shouldn't be using this dropper. Should be using this. Okay. So the first
I think
thing
I'm missing a colon as well. So there's an indentation issue.
Yeah. Thanks. So we're going to keep adding stuff over here as we go on. So the first thing we'll add is number of source vocab, and then this is because we're going to need this, and then the this is because we need to embed our encoder and decoder inputs and targets. Okay, so embedding is equal to nn dot, and it goes from num source vocab to our embedding dimension, and then similarly we'll have self dot decode. Okay. That's the first step. The second step is to get the positional encodings. So self dot encoder positional encoding is positional encoding, which we've already defined. So it starts with embedding dimension, just key model. So embedding dimension, and then goes to max length, which we haven't defined. So we're just going to put those two numbers in, which is max source length, and then max target length. In our case over here, what we have done is we have made things easy for us. We have said that, okay, only length 10 would be used, but you can use variable lengths, and that's why we're putting it this way. So it stays fairly generic. So it's max then, and then similarly, and this is why we have to define two different positional encoding for both. Actually need we're going to use the same dropout also. Okay, so that, and then similarly we'll have decoder positional encoding. So this is how you would actually do if you have to create a transformer. It again goes from embedding dimension to max target length, and then actually let me just copy and paste these two directly, and we just change this to target. Okay, so now this is okay. So now we have done the positional encoding. The next step is to create one encoder layer and one decoder layer, and once those are there, we'll create the encoder and decoder stack by stacking n of these together. So we have encoder layer is equal to nn dot. Actually, now you can start copying stuff and just change a few things. So we have the encoder layer here. So that's our encoder layer, except this. We change to this. It will add number of heads and hidden size, everything together. So we have hidden size over here. We need n heads in this. We need n layers in this. So that's the only thing which we need. So this is n heads. This is hidden size, which is hidden size, and then dropout is dropout. Okay, similarly, you can just copy paste this again and create a decoder layer because the arguments are same. Now we'll create self.encoder is equal to nn.transformer encoder. It takes the encoder layer, and the number of layers is equal to n layers. Similarly, we'll have self.decoder now. And we'll have the decoder layer and layers of that as well. And finally, what we need is just the output dense layer. So self.output is equal to nn.linear, which goes from embedding dimension to num target vocab. And that's it. So this is all what we need for init, and now for our forward. So this is where we'll start making all the connection forward. And then target. Okay. So now we so the first step again was our creating the embedding. So source is equal to self.encoder embedding, and then put source in it. And we're also going to add a permute to this. So permute 1, 0, and we'll do the same thing for target. Instead of source embedding, encoder embedding, we'll now have decoder embedding, and this will become target. Okay, so embeddings are done. The next step is to have the positional encoding. So source is equal to self.encoder source, and then target is equal to self.decoder position encoding, which will take in target. So those two are done. Now we go back to the diagram. So this is our input, this is our output. We embed both of them. We do positional encoding for both of them. Now we'll feed this input to the encoder stack, and the output of the encoder stack and the target will go inside the decoder stack. So that's what we'll do now. Going back to this. So we'll do memory is equal to self.encoder, and it takes in the source, and then transformed output is self.decoder, which takes in the target and the memory.
Devansh, so there is a typo in the decoder in init.
Where?
In init, under init, you have a typo in the decoder word, self.decoder.
Oh yeah, I see. Thanks. So yeah, that's done. And now all you have to do is just to map this to the vocab. So I can just do return self.output and then put in transformed output inside, and that's it. There's one more step which we can add, which is log softmax. So self.log softmax is equal to nn.log softmax. So output is this, and then return self.log softmax output. Okay. So this is what we have sort of done. We took the inputs, embedded them, position encoded, fed it to the encoder, targets, embed them, position encode them, taken the encoder output and this, feed it into the decoder, apply a dense layer or a linear layer, and apply softmax. In this case, this is a log softmax, just because, again, your your vocab size is large, so you want to be sure that when you're computing probabilities, you don't run into numerical issues. So so it's better to use log softmax instead of softmax. It's just applying the log function on top of it, nothing special or extra on top. Okay, so that ran. Now we need to sort of fill in these values and just initiate our transformer. So that's fairly easy. What we can do is we can copy this whole thing as it is and then start filling in values over here. Okay. Okay. So the number of source vocab is fixed. This is the English vocab size. Similarly, we'll have this, which is the EU vocab size. Okay. And for the embedding dimensions, this is also fixed. This is embedding dimension. Hidden size is also fixed, which is hidden size. Number of heads is fixed, which is called num heads. Number of layers, which is how many encoder decoder are there in the stack, which is num layers. Max source length and max target length is also fixed, which is max sentence length. So this is max sentence length. And as I said earlier, we made our life easy by just sort of fixing that we won't go beyond 10 sentences and everything will be padded to 10. And this is just drop out. So if you initiate the model and hopefully everything goes right, and yay, it did. Okay, so this is our whole model. Okay, there's embeddings, there's positional encoding, then there's transformer encoder, there are multiple encoder layers. So now we have decoder, we have multiple decoder layers, and then finally we'll have a linear layer and the log softmax. So that's our transformer, which is as shown in the figure. So code it up. The next step is to create a training loop. And this is where we just go back to our first lecture or every lecture after that. This is how you create a normal PyTorch training loop. There's nothing extra in all this. We'll only create two, we have to create two more things. So one is the loss function, which is nn dot n, which is, so if you have, so the loss is cross entropy, but if you have already done if you have already taken your output into log softmax space, you use NNL loss, which is the likelihood loss, which is softmax. So cross entropy is softmax, log softmax plus likelihood loss. So this ultimately is just cross entropy if you remove that layer, the last layer which we added. Okay, and optimizer will again keep a simple by using optim.atom, and here we'll just put model.parameters, and learning rate is already defined for us. Just this. So that's it. It's all standard stuff which we have done. This is how our training loop usually goes for epoch in number of epochs, and for index comma x comma y in the train loader. Okay, so we'll do what we do for all our training loops. We'll first put everything to the GPU. So this is actually, should also put model to the GPU. Model is equal to model.to. So while the model is going on the GPU, I'm gonna code up the rest of the things. Okay, so now all the data is on GPU. Our output will be equal to model, and it takes in two inputs, the source and the target, which is x and y. So that's easy. Now we compute the loss, and for loss we need so the loss is equal to the area takes two things, the output, but the output has to be permuted because again dimensions So this has to be permuted to, I think, 0 to 1. Let me check. So it's 1 to 0 again. And this will compare with y. And then it's very simple, loss dot backward optimizer dot step. And we'll just keep adding loss to, so current loss plus equal to loss dot items. That just sort of brings the loss value down from your, one thing we also need is optimizer dot zero, right? Loss dot backward, optimizer dot step, find the loss value, and then finally loss trace. So this is just a place where we'll be appending all the loss values. Each epoch. This should hopefully work. Okay. Something got messed up somewhere.
It should be permute, right? Criteria output dot permute.
Oh yeah.
Also, the intent of loss trace is a little bit weird.
Actually, this is all of this has to be okay. So now it's training. It's gonna take about a couple of minutes. So I've tried training this several times, and every time it gives me a new loss curve. So let's see how it goes. And I'm going to talk a little bit more about what people actually do to train these transformers. As you can see, we have created a very small version. People usually create, for example, the dimensions are much larger. The number of layers may or may not remain same. And training these models could be incredibly hard. So right now what we are doing is very simple. But once this sort of finishes, we still have about 20 minutes so we can talk about what people actually do to train these models and how typically these models train for several hours to days. Okay, meanwhile, the loss looks nice, which is sort of good. But what we can now do is we can test out our transformer. So we had a split between our data for train and test. So we also have a test loader, and this is what we've sort of written up over here. And when evaluating your model, you do not want it to compute gradients or remember gradients or whatever operations it's doing. So that's why we have torch.nograd over here. And this XY is same, which is coming from test loader instead of train loader. Now we put it on the GPU and then run it. It just gives you all the output. I'm just gonna add one more thing over here before I run this, and that's output is equal to dot permute, because we have to 1, 2, 0. Okay, this is, run this first, and now we run this. Now this has given us some output. So if we do x dot shape, y dot shape, and outputs dot shape. So we have x dot shape, which is 128,10, which is our batch size, 10. Similarly, y dot shape, and then the output is 128,6892, which is the vocabulary length, 10. Okay. So what we have to do is we have to take like a argmax along this dimension over here. So what we'll do is we can copy this thing from the top where we were printing source and target values. Yeah. This is the first thing we'll do. So this is X and this is Y now. Okay. So this is what our source and target look like. So it says, Tom took CD out of its case and then whatever the translation there for that is. Okay. And then we're gonna add /n model output, and then for index in outputs dot argmax. So wait, output 0 dot argmax 0. Yeah, that should do it. Print. This should work. Yep. So this is what our model did. So I think it got everything fine, more or less still here. And then these two, actually this word is different. So you can see it's working. It's doing something which looks like which looks reasonable right now. But I won't sort of guarantee or say right now that, okay, if you run it for longer, it's going to do better. And the reason for that is people do something called learning rate scheduling, which is they change the learning rate as they're training, as they're training further. And that's what helps to train these large scale models. So since we have not implemented any learning rate scheduling over here, running it for longer or running it for larger number of epochs probably won't help you, and it may lead to model diverging instead of converging. So there are a few things which needs to be added, but this is what I sort of have for you. I'm just gonna go over it once about what I've done, and then we can have questions and wrap up. So we started with language translation tasks. So in this case, we have German to English. This is what we have been doing for the last couple of sessions. We take all the data. We say we'll only look at sentences which have a maximum length of 10, or that's where we'll chop it off. If they are not of length 10, we'll pad it. If they are of length 10, we'll just chop it. We take that, we tokenize it, and then we sort of embed it later. So once that is done, we define some hyperparameters. We convert this whole thing into a data set so that we can ingest it using Torch. And then this is what a sample sequence looks like. This is start of sequence, end of sequence, I don't like swimming, and then German translation of the same, and then padded to make it length 10. And then the rest of this whole session was sort of concentrated on building this whole architecture. We take in the inputs, embed them, position encode them, give it to a decoder layer, and apply n such layers. And while training, your model will learn all of these things. We also have the second part, which is outputs, which is also shifted, which is also embedded and then position encoded. And your decoder takes the output from your encoder and the input. You have n such decoders stacked together, decoder layers stacked together. And the final output, you just apply a linear and a softmax to get the output probabilities. And whatever we get out as the output, it's of the same length as of our vocabulary. So we just apply a normal cross entropy loss. And we just train it using our more or less normal transformer, the normal training loop which we have for any of our PyTorch codes. And this is what the loss looks like. And this is, yes, what the answer looks like for one sequence. I can try it for other sequences and see how it goes. It may or may not work very well. So yeah, so we have another sequence now. It did, okay, so it started doing this thing which we were laughing about before the session started. So your source says Tom made it look effortless, end of sequence, and then it's padded. Similarly, the German translation, end of sequence and then padded. Our model has right now not learned that after end of sequence, you're not supposed to do anything. So even after end of sequence, it's trying to predict something and then padded. But the first couple of letters looks good. And this, I think, is doing incredibly well for just like 5 minutes of training. So I'll be happy to take more questions for the next 10 minutes. We'll be also happy to take any comments or feedback for improvement.
Yeah, so in the previous cells, you had two inputs, target and memory for a decoder, contrary to a single input in the encoder. Yep. I'm assuming this is inbuilt in the nn.decoder layer. Could you explain this part of the code again when you have a chance, please?
Yeah, okay. So that thing is inbuilt in So this is how the architecture is. So this one whole box is a decoder layer, and this is how it is already inbuilt. It takes in this, which is the output from your encoder, and this, which is the target. So it's already inbuilt. What you do is you take in your target, you apply a multi-headed attention on top of it. This is self-attention, and then here here the key and the query and the values are the same, which is the target values. You add a norm, and then there's a residual connection. All this is already sort of taken care for you inside PyTorch. The next thing is this goes in, and now you have multi-head attention, which is coming where key and value, where key and query pairs are coming from your encoder. So this is what goes in. You apply a multi-head attention, again, take this as a residual connection, add a norm, and then finally a feed forward, which is similar to this. So there are two inputs, and yeah, the architecture sort of takes care. Like NN.transformer decoder layer takes care of it for you. Yep. So that's all from my side. Shiraj, if you have anything else to add, Susanna, if you have to add anything else. Thanks, everyone. We'll see you again in 2 weeks. We'll be talking about GANs, and have a great weekend.